Now we will see fins of different profiles. So far, either rectangular fin or fin of circular cross section, they have uniform cross sectional area. See, AC, which is W by D in this case, is constant, or it is constant throughout the length of the fin. Whether you find here, you cut a section here or here or here or here, wherever, suppose it is shown as it is shown here, the dotted line. At that place, what is the cross sectional area? W2. So AC is independent of X. Suppose if you take this section, is it so? No. So here thickness, this dimension, whatever this dimension we call, is more. Now this dimension may be same throughout. Now you see cross section here. This cross sectional area is more if you move to the left side of this, is less if you move to the right side of this. And if you see the tip, it is 0. Right? So therefore the cross sectional area is not constant here. If you take this case, is it same or will it be different? In the direction of R, AC, same? Same or not? It's not same. Why? Radius is increasing. Suppose if you take section here, you consider only radius up to this point. You move here, radius increases. Right? What about this? Same or different? Different. Varies. Right? So therefore, whatever the formula that we derived earlier cannot be applied to these cases, or cases like this. Because our assumption was AC constant and we brought it out of differentiation or integration as the case may be. So therefore, those formulae cannot be applied to any structures like this. Now, how to solve such problems? And there is a prescribed procedure for this. Of course, you can do it, and each of these cases you should consider separately and then solve it. Now you should be knowing what is the diameter here, what is the diameter here, and how the diameter is variable with the x, right? So accordingly you take the AC inside the integration or differentiation and then do it. Right? There cannot be one single formula which suits all. Each case is different, okay? Because the nature of changing cross-sectional area is different. So now the simplified procedure for this is to use data tables like this, where you can find for a given profile or given field. On the x-axis, it's a combination of characteristic length, h, k, am, which you all know. Where am is new parameter here, which is called profile area. Profile area is what is visible in the front view. Suppose this is triangle. Forget about this base and the remaining part. If we take this is triangle. And what is the profile area of this? Half into L into T. If L becomes LC, half into LC into. Now what is the profile area for this? L into T. Remember, profile area is perpendicular to cross-sectional area. Earlier, you see now I am talking about this is the profile area. What is the cross-sectional area? This is the cross-sectional area. Right? So cross-sectional area is perpendicular to the direction of heat flow, whereas this is in the direction of heat flow. So they are mutually perpendicular. So simply one thing you remember, if you see it in the front view, right, you see the side of the fin, and whatever shape you see, that is the profile area. So here this is a triangle, this is a rectangle, and then while starting the discussion we called it as plate fins of uniform cross-sectional area, right? Uniform profile area. So now you can find this x-axis because this is given data, and for this shaped fin, say triangle or this shape rectangle, corresponding curve should be taken. Suppose if my value of this combination property is 1, then I project it into, suppose my fin is triangle, then I look at this. What is the efficiency now? Approximately, let's say 70%. Right? So this data is prepared with some mathematical formulation. So that's for users' convenience to help you solve such problems.